Hello, my name is Dilip, and today I am going to talk about one of my latest work in PostgreSQL, which we are trying to get it into community, maybe for PG19. Means at least earlier we tried it to get it into 18, but once we tried implementing it, we realized that why it was so difficult project to get into the PostgreSQL in past so many years, where many people have tried. There was past lot of discussion in open source community, and many people were in opposition also that they might not want global index in PostgreSQL. They have their own reason, and we can discuss that as well. So while we experimenting with that, we realized that why it was so complex and what all complexities was there. So I would like to take you to step by step where we can discuss the design decision we have taken and what is the reason behind those decisions, and ultimately where we found the maximum problem or what design problem we faced. Because of that, we could not even submit it for PG18, and we might try for next version. Still, it is in experimental phase and POC phase, so I will not say it's quite ready, and we cannot guarantee when it can actually get committed to PostgreSQL. So this is going to be agenda of my talk. First, I'll quickly touch upon what is table partitioning and limitation. Like for understanding the global index, the table partitioning is one of the key factor. And then I'll briefly talk about global index, that how it can help to get over those limitation what currently PostgreSQL have in partitioning, and how other vendor like Oracle do not have those issues. Then I'll go into when we were starting this project, what was the high level goals, so that the goals are not only related to making it the best product, but also it should be acceptable in community, and it should have a minimal impact on the current system. So that is what I want to share in my high level goal. And then we will talk about the design. In that, I'll cover the storage. The major key parts are storage of the global index, and how the attach and detach partition can work dynamically, because we can attach and detach partition in PostgreSQL anytime. And then we'll discuss how the global index scan is going to work, how the planner optimizer will select that scan path. And ultimately, we'll discuss the design challenges we have faced, which are still, many of them are still open. Okay, so table partition is nothing but when large tables are divided into a small piece, which we call partition. In PostgreSQL, those partitions are also a table. And in other databases, those could be just a storage piece, which is storing data, and might not be directly user accessible table. So each partitions in PostgreSQL are stored and managed separately as a table, but ultimately for a user, you can think it as a one big large table, which is stored and managed separately. So limitation, what I want to discuss here, and for which we want to discuss the concept of the global index, is we cannot have a unique constraint on non-key column. I'll come up with the example also, but that is the main limitation, that if you want to have a unique constraint, either you need to add that column as a partition key, or you need to add a partition key to that index. Independently, that column on any other column which is not part of partition key, you cannot add a unique constraint. Okay, so here I just give a small diagram also to explain the idea, that what is the difference between what PostgreSQL currently have and what we are trying to get. So currently PostgreSQL have a partition index. It means like how your table is partitioned, each partition will have their own index. And the reason why we cannot have a unique constraint across the entire table, because we are getting the unique constraint by structure of the index, right? This is our index. Suppose, for example, it is B tree index. So how B tree is stored in the order of the key, with that property we are getting and guaranteeing the uniqueness. And if every partition have their own unique indexes, we cannot guarantee the uniqueness across the partitions. That's the property of the how storage is done. And global index reduce that by providing a common index which will store a data from all the partition within a single index. And that now, by the nature of this index, you will automatically get the same property what you are getting within each partition. Now you'll get a cross partition. Okay, this is the example what I want to explain that why we might feel it is a practical use case to have a global index. So the first case where we are we don't have global index. In that case, suppose you want to get a unique constraint on the user ID, you cannot get. If you try to create a unique constraint only on the user ID, we are going to get an error. That unique constraint cannot be, unique index cannot be created on non-partitioned key. So I need to add this extra column, which is a partitioned key, because table is divided by that partition. But don't you think it is very limiting, because the user who is creating that partition or creating a partitioning for that application, they want the data to be stored by the region. They don't want user ID to be in that region, right? They want to store the data by region. And they want a unique constraint also based on the user ID. But that you cannot achieve here. If you are adding user region here in the unique index, it means your user ID can be duplicated across the region. So that is not the requirement. So although I agree that global index somewhere, and some of the part of the argument why people don't want global index in PostgreSQL is, it is actually working in opposition of the partitioning requirement. Partitioning means we are dividing a data, we are partitioning the data. And you are saying that we want a global index which is actually merging the data. So it is actually the contradictory work, and that's the reason many committers don't agree that global index is a good idea. But for these kind of use cases, if you have this use case, either you don't use the partitioning or you need to live with the limitations. So that's why I think the global index are useful in these sort of cases. I will not say we need to use the global index everywhere with the partitioning, but somewhere it is unavoidable. So these are our high-level design goals, and mainly the design goals come with thought in mind that we want to get it committed in 1 or 2 versions of PostgreSQL. We don't want to work on this forever or for our lifetime. So that's the reason those goals are there. So first is, we do not want to change the storage format of the B tree. We don't want to change the on-disk format of the B tree. It will get clarified once we go into the storage that why I am talking about this particular on-disk format change and how it is relevant for the global index. But that is our one of the main goal. Otherwise, we have to copy a complete B tree and make a new access method, and maintenance will be very, very difficult. Second thing is drop and detach partition. We do not want that when anybody want to detach the partition or drop the partition, whole global index need to be rewritten or need to be blocked, and we need to take out the data which are related to the detached partition. So the cleanup of those, it should be we should be able to identify that those data which belongs to the partition which got detached are not relevant now somehow, but we don't want to block and do that cleanup right when we are detaching. That is one of the goal. Another goal is, the B tree have certain property like suffix truncation and deduplication kind of compression, and we do want those compression and property to get us for free instead of putting a lot of extra logic. And this part also, once we go into the storage, we can understand better. Okay, so now we are jumping into the design part of the global index, that how we implemented the global index. Okay, so global index is a single table, single index across all the partitions. In PostgreSQL, how index is designed, index have a key and the tuple identifier. So you have key to search the key into the index, and you have a tuple identifier. Through that, you can locate the tuple into the heap. And tuple identifier is nothing but the block and offset. So that's enough for the normal index. But do you think it is enough for the global index? Because global index is storing the tuple from multiple partitions. So if you say block and offset, that is duplicate across the table. So for that, we need an extra identifier. So we want to locate a partition inside that block and offset. So TID we need, but we also need a partition identifier. For simplicity, let's assume we can say that partition identifier can be a relation ID, but it's not true once we go more into the detail. But that identifier we need to identify which partition we have to go first, and then we can locate the tuple using the same TID what normal B-tree index can do. So in B-tree index of PostgreSQL, currently the tuple are stored in key and TID order. They are not just stored in the key order. They are also stored in key plus TID order. So if you have a duplicate key, then the tiebreaker is a TID. It means it needs to be stored in the TID order if multiple keys are duplicate. And for us, same requirement will come. If you want to get a same property of B-tree, we need to store in key plus identifier and the TID order. The same thing. We cannot change the order. We cannot say key plus TID and identifier, right? Because how tuple is located is first identifier and then TID. So how we so all the things we have discussed that we want we don't want to change the format of the B-tree. We also want to get all the property of compression property of B-trees. How we get everything for free. So what we are trying to do is here, if you see the storage, this is the how user create index. Suppose user is creating a global index on attribute 1 and attribute 2. Internally, we are adding one extra key column, attribute 1, attribute 2, plus identifier. So with that, we don't need to manage everything or anywhere like for ordering the tuple in identifier order. We don't need to do any extra logic. We just internally created extra key. It means Postgres tuple are automatically stored in key order plus TID order. Now our tuple will be stored with key plus identifier order because we make identifier also as a key, which is internal key, but once we expose tuple outside to user, that part is hidden. Okay, so let's discuss what is that partition identifier. So as I told that maybe in some simple term, we can assume it can be a relation ID because we just want to locate which relation that tuple belongs to. But actually, we cannot use the relation OID, and reason is that you can actually detach and attach the same relation multiple times. So suppose you have one relation which is part of the partition hierarchy on which global index is built. If I detach that relation and attach it back, it could happen that after detach, a lot of tuple got changed in the relation, right? And now it attached back. How do you distinguish between the existing old tuple and the new tuple? I already told one of the design goal is that when we detach, we don't want to block. We don't want to clean up the old tuple. And if we are not cleaning up the old tuple, then the tuple which belongs to when the relation was part of the partition hierarchy before, after detach, and now detach and attach again, we won't be able to distinguish between those two tuples because they are coming from the same relation. So that's why we implemented a new identifier called partition ID. And the mapping between the relation ID and partition ID is stored into a separate system catalog called PG index partition. And how we are avoiding the need of cleaning up the index while detaching is by this one, that every time you detach or attach, we are getting a relation is going to get a new partition ID. So it means your relation is part of the partition hierarchy. You detach it. We can leave the tuple as it is, and you attach again, it will attach with the new partition ID. And once you are scanning the global index, if you find the partition ID which belongs to the relation when it was part of the global index at previous time before detach, you find this mapping in this one is gone for that particular partition identifier, so we can ignore those tuples. We can ignore or we can do a cleanup like killing, but I think currently we are not thinking of killing it immediately. Instead, we are doing some sort of like bottom-up deletion and simple deletion is there. So if we are in need of splitting the page, at that time we will just look up the find into that page and see if partition IDs are there which don't point to any relation. We can clean them up. Okay, so there is one more thing to partition ID. That at a time, first thing is that we need only partition ID for the leaf relation because only leaf relation have the tuple. Intermediate relation or top relation, they don't have any tuple, so global index don't need to bother about storing any partition ID for them. So here, each leaf relation cannot just have a one partition ID. That is one of the requirement. And reason is that global index can be at multiple level. In this, maybe that is not a very common use case, but once we are implementing that, either we can restrict that we can create a global index only at the top level of the partition hierarchy. But I think we can easily get this flexibility, so we thought of implementing that also. It's good to put fewer limitation than more limitation if you want to go and get into PostgreSQL. So that's one of the reason. So yeah, now there are two global indexes there. And if I get a same partition ID for any of the leaves, suppose consider a table T22 is there. If I get a partition ID 1 for that table, it means for each, both global index is storing that partition ID 1 for tuple related to T22. And if this partition hierarchy get detached from here, from the T2 itself, it means the T2's tuple which are inserted into G is invalid now. They don't point to anything. But those tuples, same tuple of T2's in G2 are still valid because it is still attached to this global index. So that's the reason if I get a same partition ID and store the mapping in PG partition ID that this partition ID 1 is pointing to T22, that's not valid. So what we want is, we want a combination of global index and a partition ID to map to some relation. So now I need to get a two partition ID, one for G and one for G2 for each leaf relation. Okay, so this is how the mapping looks like. This is before detach. You can just keep that diagram in mind that we are detaching it here from T2. So this is the mapping that all leaf relation with respect to G is having some sort of partition ID 1, 2, 3, 4. And for the G2 also, the same table which are coming under the G2 are having this partition ID 1 and 2. Those T11 and T12 are not coming under the G2, so they are not having any mapping for G2. Now after detach, these mapping of partition ID 3 and 4 from G got invalidated. They are not pointing to anyone. So if I come and scan the tuple of partition of table T21 and 22 in the top global index, I will find it is pointing to nothing. It means we don't need to do anything for this tuple. We can just ignore them. Okay, let's discuss about a second part, which is related to attach and detach. That what we need to do for in case of attach and detach. So at any level in PostgreSQL, you can like attach a partition. You can attach a single partition. You can attach a group of tables, which is in itself is a partition hierarchy. You can attach it to any level. So what we need to do for attaching, for logically we want to get a partition identifier of each leaf relation, right? If you're attaching either leaf relation or you're attaching a whole partition hierarchy, under that leaf relation are there, then we need to assign a new partition ID for all of the leaf relation and insert the mapping into PG index partition catalog. Then we need to rewrite a global index so that the new data can be loaded from the attached partition. So this is one of the contradictory thing that we can think of a different design. While you are attaching a partition, when you are attaching a partition, either you can rewrite the global index, it means the data will be automatically loaded. On the other hand, you can just read that table, whichever you are attaching, and from that you can insert the data one by one into the global index. The only problem is that either this can be a decision on the runtime based on how much load is there, because sometimes rewrite might be better, because the partition what you are attaching, under that there are a lot of partitions are there and a lot of data are there. So rewriting the whole global index might be better, because you can just sort and load data into the global index. On the other hand, if you are just attaching a single partition, at that time inserting the data from that partition might be cheaper. And the second part is detached partition. So as I told that our goal was at the detached partition, we don't want to do anything. It means we just invalidate the mapping into PG index partition. It means as soon as you invalidate the mapping in the table, all the tuple which belongs to the detached partition or partitions become invalid automatically, and scan can ignore them. They need to look up into the PG index partition. We maintain a cache over that, so that lookup is very, very fast. Just the one hash cache is there.
Each tuple of that partition need to keep going there.
Yes, yes. Okay, so this is how global index can work. So in optimizer, we need to consider the path, a new path for the global index. So currently, when you have a partition table, they don't get a path by on themselves. They need to get a path on the child relation, and on that they can create append path. So that is how the partition table get a path. But this is a new case where partition table in itself can get a path, because they also have their storage with in form of global index. So we are considering this new path for the table which are having the global index on them. And there is still one limitation we are putting, that we are not considering the path for the child relation if they don't have the direct global index on them. In this case, you can see T has a global index G. On that, we will select global index scan path. But when you are scanning on T2, we do not even evaluate the global index path, although logically it is possible, right? Because when you are scanning T2, you can put a filter in the global index based on the partition ID. You can put whatever partitions are covered under T2, you can just say, along with the key, only give me the tuple which belong to these partitions. So global index is possible while scanning the underneath table also. But only problem is we are not sure about making this costing infrastructure change, where we need to consider that whether selecting whether our target is just a partial data, still we are going to scan a global index which is holding the data across whole partition hierarchy, will be even logical or not. So that part is still consideration, but we are currently not evaluating those paths. So only if global index is there directly on the table, that time global index scan path will be considered. So during scan, as I told that each index tuple in the global index will have a partition identifier. And when we find the partition identifier, we need to, because anyway, when we are doing the index scan, if you have to go to heap, that time we anyway need to look up the heap pages. So at that time, we have an additional lookup into the cache to convert the partition ID into a relation OID, and then we can go into the relation. If you don't need to go into the relation, if it index only scan, you don't need to convert partition ID into a PG index. You don't need to convert the partition ID, or don't need to look up into the mapping. Okay, so here are some of the design challenges. There were a lot, but I'm going to share some major design challenges we have faced with the global index. One is related to vacuum and the locking redesign in the way how PostgreSQL currently do. We need a lot of different design in locking. And also there are some of issue related to DDLs like alter tables and altering the tables which are at the lower level on which the global index present. So this is one of the, so vacuum, for explaining the vacuum problem, I would like to start with a test. So what I did is, there was 1,000 partitions. Each partition were holding 50,000 tuple. Then we vacuum that table, two set of table, one table where we are only having a partition index. On the other hand, other case where we were having a single global index, no partition index. So without global index, it took a 15 second, whereas with global index, it was 45 minutes, and that was the eye opener that why it is really hard problem to do the global index in PostgreSQL. Reason is very straightforward actually, because you can see when you are having 1,000 partition, your partition index, each index is of certain size, which are holding a 50,000 tuple. Your global index is holding all the tuple. So it is 1,000 times bigger than any single index or any single partition index. And that is not very easy or straightforward to solve, because in PostgreSQL, the design of vacuum is that heap and index vacuum are very tightly coupled. You cannot do them separately. We have a fixed set of steps, like first you do the heap scan, collect the dead tuple, and then you vacuum the indexes, and after that only you can reclaim those dead TIDs and make them reusable for the future insert and all. And global index also, as of now, without, if you don't do any modification, is considered as a normal index, and it got vacuumed every time with every partition. So it got partitioned 1,000 times. So you can see this time is 200 times more than with the partition index. Although it is not 1,000 times more, because the same global index is vacuumed multiple times. So every time the cost of vacuum will not be equally high, because some pages will be in memory, some dead tuples are already clean, but still it is being vacuumed 1,000 times, and that's the main problem. So yeah, this problem must be solved before we even consider to submit it to PostgreSQL, and there was two solutions we considered. One thing is vacuum the global index only once per top level partition. Of course, very obvious solution, right? Means why we want to vacuum the global index 1,000 times, just vacuum it once. And second thing is decoupling of the index and heap vacuum using some architecture which is already submitted in PostgreSQL, and people who are connected or following the mailing list, they might be aware that what is that conveyor belt storage. Not very straightforward here. So if you decouple index and heap vacuum, then they are not together, right? It means you have an independence of, you can decide when index need to be vacuumed. When it is in need, it will get vacuumed. So we don't need any specific solution for the global index. I'll come into this solution, then we can discuss in more detail. Okay, so first thing is vacuum global index once. So currently, for auto vacuum worker, they don't consider any partitioning logic, and that might not be required as of now, because for them, each table are independent, and they just make a list of tables which are in need of vacuum. And if that table is not being vacuumed by any other worker, I'll just go ahead and vacuum it. That's the simple logic of auto vacuum worker now. But with global index, what we need to change it something, right? We want to ensure that when you vacuum all the 1,000 partitions, they should vacuum global index only once. It means that is not very straightforward. You cannot just do that, because you need a dead tuple IDs which you have collected by vacuuming heaps. So it means auto vacuum worker need to know that which all tables are coming under the same partition hierarchy. We already, that part is not too difficult to know, but we cannot make a list of independent table. Instead of, we need to make a list at the partitioned table. So if any partition table have a global index, we will not collect their child. Instead, we collect the partition table. And underneath vacuum machinery, we'll send that partition table directly. So what it will do is, it will open up the table, get list of all the tables, vacuum those tables one by one, vacuum local indexes also, but it will skip the global index. It will skip the reclaiming the dead TIDs, right? Unless you don't vacuum the indexes, you cannot reclaim the dead TIDs. Otherwise, index will point to somewhere in garbage. But we need the dead TIDs. So we store that dead TID store and create a hash map over that. So if you have 1,000 partition, your hash map, you assume have 1,000 entries in the hash map, and each are pointing to one dead tuple store. And once we got 1,000 dead tuple store into that hash map, and all the partitions are vacuum, we are going to go and vacuum the global index only once. And there also one infrastructure change is required, because now it is not that single dead TID store where we need to look up from the index that whether the tuple is deleted or not. Instead, we need to look into the hash map and identify which dead tuple store to look into. So first we need to convert those tuple using the partition ID into a table ID, and then we can look up into the respective dead tuple store. So this have infrastructure changes, but mostly code redesigning and reorganizing, but we don't need to build any new infrastructure. And once these all steps are done, global indexes are cleaned up, we can reclaim the dead TIDs from the heap. Again, we need to send each heap to for the vacuum, only the last phase where we just need to reclaim the dead TIDs and mark them reusable. Okay, so what is the problem and benefit of advantage of this solution? So first thing is, we don't need any new infrastructure. We just need a lot of redesigning of the code to do that. So implementation cost is low, so we can consider or propose this as a first solution, provided it is being accepted. The problem is that as I told, that now auto vacuum is not operating at the table level, they are operating at a partitioned level. It means all the tables which are covered under the single partition hierarchy will be vacuumed by the same worker. So you got a limitation, right? Earlier those tables could have been being vacuumed by multiple workers parallelly, but that concurrency you have lost. So assume that you have only one partition table with the global index. Under that you have 1 lakh partitions. So everything need to be vacuumed by a single worker. You don't have flexibility to distribute across the worker, because then again you need a new mechanism to store the dead tuple, store into the shared memory, and all this new infrastructure we need to build. So with this solution, what we are trying is a simple solution in that limitation will be there. And another problem is that since our goal is that we don't want global index to being vacuumed multiple times, it may so happen, right? Currently, PostgreSQL pick the table which is ready for the vacuum. It have suppose reach certain threshold of the dead TIDs, number of dead TIDs or number of inserts or updates, then it get picked for the vacuum. It may so happen that currently only one partition is ready for vacuum, then second partition is ready for vacuum, then third partition is ready for vacuum. That means every time you collect some dead TIDs, dead tuple, and vacuum the global index, it means global index again going to get vacuumed multiple times. So for avoiding that problem, what we are doing is, even though some table which are not ready yet for the vacuum, they are just reached the 50% of the thresholds or 20% of the threshold, those are also getting picked and becoming a victim of the vacuum, that we need to vacuum them also, so we can avoid a frequent vacuum of the global index. That is the two major problem I see with this approach. Okay, this is the second approach what we are trying, decoupling of index and heap vacuum. So as part of this approach, we don't consider that when you vacuum a heap, you must have to vacuum an index. And what is the reason that we have to do that? Because the dead TID store is the reason, right? We are storing the dead TID store into a local storage. You vacuum the heap, you collect the dead TIDs into dead TID store, and you vacuum the index. But what if we can remember those dead TIDs for the long time, somewhere in the persistent store? It means we are not bound to vacuum the index right then and there. it means your that TIDs can be stored across the vacuum cycle. So what we need with this solution is that we need to improve, or we need to at least make the scheduling algorithm aware of this decoupling. Like currently, what scheduling algorithm does, it don't have any prioritization between the heap. It just pick a table. If it need vacuum, it will send it for the vacuum. It doesn't consider that any other table is there which is in more need of vacuum compared to this table. There is no comparison between these. If you need vacuum, I'll send you for the vacuum in the just PG class scan. But when index is also there, heap is also there, how that scanning will happen, how this prioritization will be happen, whether when we need to schedule an index vacuum, what is that time? So you cannot see, if you have done the decoupling, it means you cannot just blindly scan the heap and find, okay, it need a vacuum, vacuum it, then just take all index of the heap and send for vacuum. Then this whole point of decoupling is gone, right? It will just help the global index, and it will not help improving the normal vacuum of the PostgreSQL. So we need to come up with a better approach, because index are getting cleaned up by themselves also by many other mechanism during bottom-up cleanup and simple cleanup during page split. So we need to consider that factor. So we need to identify that vacuum of the index should be scheduled only when it is in need of the vacuum, when it have enough dead tuple, and when enough dead tuples are collected from the heap and that index is not yet cleaned, then we need to schedule the index vacuum. And if you get that scheduling algorithm right, then we don't need to do anything for the global index. It's completely free, right? Because global index is 1,000 times bigger than a normal index. It means it will reach that threshold of having the dead tuple much later than the normal indexes. It means it will automatically schedule delayed compared to the normal indexes. So everything will be automatic. We don't need any specific consideration that global index need to be vacuumed only once. Okay, so it will improve overall vacuum infrastructure, not just limited to global index. As I told, you can make whole scheduling different. You can consider your logic for freezing or wraparound, that which table is in need of wraparound. You can schedule them first, and you can see which index have more dead tuple. You can put that index after some random heap, because dead TIDs are stored in the persistent store. You don't need to order them in sequence. And no specific handling is required for the global index, because that's based on the stats, nothing. And problem is that we need a very big new infrastructure for preserving the dead TID store. Although it was submitted in Hackers long time back, I have worked on that algorithm to decouple the heap and index vacuum, and I know that problem is equally hard. Like currently we are talking about how hard is the global index, but that problem of decoupling is even harder, because decoupling you can avoid index vacuuming on just after the heap vacuuming by preserving those data into the persistent store. But problem is that getting that scheduling algorithm right, or convincing or getting everyone on board with that scheduling algorithm is really, really hard, right? There are a lot of algorithms are there, a lot of priorities are there, which heap to vacuum first, whether the heap which is in more bloat, you need to vacuum that first, or the heap which is in that verge of the wraparound, you need to vacuum first, right? So taking that decision, and then the timing come into picture, that currently the bigger table might take a longer time to vacuum. Then the next table which is at the verge of wraparound, how much time it will take to get wraparound. So based on that, we can ordering. So it's really very, very hard problem to solve, which we can just work around it and come up with a simple solution, but it's not very easy to get the simple solution into the PostgreSQL. It should be completely logical. Okay, another part is about locking issue. So this limitation, this problem actually comes because of our capability of PostgreSQL, that you are allowed to directly insert into individual partition. Most of the other vendor in Oracle and all, you cannot consider each partition as an independent table, so you cannot directly insert into those. But since we allow that, we get a major locking infrastructure problem. And that problem is related to because in PostgreSQL, if you directly operate on the leaf relation, you can just insert into that table and get away. You just need to lock that table. But now, if this global index exists on somewhere on its ancestor or its parent, you need to lock the whole partition hierarchy. And reason is that the main reason we are getting global index is for the uniqueness check, right? And when you are scanning the global index for inserting the tuple from one of the leaf relation, it may so happen that you found a match, a duplicate, but you need to check a snapshot whether that tuple is still valid or not. And for checking that, it might belongs to any partition, right? It doesn't mean that it will belongs to your partition. It can belongs to any partition, so you need to lock all of them. And that locking infrastructure, we need to make a lot of change in optimizer because of our all locking decision that what table need to be locked and making a list of relations on which your plan depends. Everything happen in optimizer. So we need to maintain those different lists for the locking. So that infrastructure is also quite complicated. We have a POC for that, but it's not yet mature. Another option is that we can disallow operating on the leaf relation if global index exists. And yeah, most of the people who are demanding global index are migrating from Oracle, and that things are there in Oracle as well. So we need to see that how those limitations are acceptable by the open source community or not.
But all our operations are always on the leaf table. Partition.
Partition, if you insert in the partition table from the top level, it will ultimately go route to the leaf level, but at that time optimizer consider to lock everything. But since you directly operate on the leaf, that time optimizer don't take care of locking the whole hierarchy, and that where we come into the problem.
But there, Postgres mostly we are tuned to directly insert in leaf.
Direct means user directly operating on the leaf. Yes, that part is there. So we can consider if there is a global index, maybe we can put that limitation, which is not acceptable by everyone. I completely agree with that. Other are major DDL infrastructure changes is required. I will not say a lot of problems are there, but there are infrastructure we need to modify a lot. Like one of the example is there, which I recently identified. Like PostgreSQL, you can attach a partition which is having different column order compared to the top level partition. And since global index is storing data from all the partitions, we have to store that mapping and conversion that where from which partition tuple is coming in that order we need to store into the global index. And similarly, while mapping back, the same problem is there. And also we need a lot of rewrite of the global index when we are modifying anything at the leaf level also. Means we can alter the column type of any leaf relation, and in that case also we need to trigger a lot of rewrite, and that also requires a lot of infrastructure changes. So I will not say it's very as difficult as vacuum problem or locking problem, but these also need to be considered. There are certain limitations we have considered with the global indexes so that we can make it simple and get it in the first version. Like first of thing is don't allow direct DML on the lower level relation if global index is there. Then we don't need to manipulate all the locking infrastructure. Second thing is restrict direct DDL on the lower level relation. When the global index is there, don't do all this alter table set that column type of the leaf relation. Instead of, you can do at the partition level. And third thing, what problem I recently talked that don't allow to attach the partition which having the different column order compared to the parent tables. Everything will maintain the same column order, only if the global index is there. Yeah, so this is summary of my talk. We discussed on that partition does not support the unique constraint on non-partition key. That is one of the major limitation which people are facing who is migrating from other vendors. And global index can address this limitations by providing the index across whole partition hierarchy. And we discussed that there are some complexities related to vacuum and mainly related to vacuum and locking. And if we disallow or put some limitation like we don't allow direct DML or DDL operation on lower level relation, like that is similar to other vendor who is providing the global indexes, then we can simplify that architecture. Yeah, and yeah, the last thing is that most of the people who are coming or demanding the global index are, at least in my knowledge, coming from Oracle, and similar restrictions are there in Oracle, not with the global index. They consider the partition is completely different way. Those tables are just a partition for them, not an independent table. So, yeah. Thank you, everyone. That's all I had.